So we're going to do another example of proof by induction here. This one's going to use the idea of a factorial. So if you haven't seen this before, given a natural number n, we say that n factorial, which we write as n with an exclamation point, is defined by n times n minus 1 times n minus 2. Keep multiplying by every natural number less than n until you get to 1. So n factorial is a product of all natural numbers from 1 to n. So to give you an example, we define 0 factorial to be equal to 1. 1 factorial is equal to just 1 times nothing, right? It's just plain 1. 2 factorial would be 2 times 1, which is 2. 3 factorial would be 3 times 2 times 1, which is 6. 4 factorial would be 4 times 3 times 2 times 1, which is 24. And you could keep going from here. All right. Now, a thing to notice is that since n factorial is defined to be n times n minus 1 times n minus 2 all the way down to 1, and because this expression here, ignoring that first factor of n, everything else is exactly equal to n minus 1 factorial, that means we can express n factorial as n times n minus 1 factorial. Just to give you an idea of what that really means here, like 5 factorial is going to be 5 times 4 times 3 times 2 times 1. But these last 4 terms here can be rewritten as 4 factorial, which means we can rewrite 5 factorial as 5 times 4 factorial. That's just sort of a handy thing to know about factorials, which will help us in the next induction proof. So, let's get on with it. Example 2. For all natural numbers n, the following equation holds. 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial all the way up to n times n factorial is going to be equal to n plus 1 factorial minus 1. Oof. Let's just try to get a sense of whether or not this is true by looking at some small cases. I'm going to just do a little bit of scratch work at the top here. So P of 1 would be the statement, just look at the first term. So replace n with 1 on the right-hand side and just look at the first term here. This would be the statement 1 times 1 factorial is equal to 1 plus 1 factorial and then minus 1. So is this true? Well, on the left we have 1 times 1, which is just 1, and on the right we have 2 factorial minus 1. 2 factorial is just 2 times 1, or 2, and 2 minus 1 is indeed 1. Okay, so this is what we'll use for the base case. This is true for the base case. Just to make sure we understand what this is saying, P of 2 would be the statement, look at just the first 2 terms on the left-hand side. This is the statement 1 times 1 factorial plus 2 times 2 factorial is equal to, now replace n with 2, so we'd have 2 plus 1 factorial minus 1. So this is going to look like 1 times 1 plus 2 times 2 is equal to 3 factorial, that's 3 times 2 times 1, that's 6, minus 1. Yep, this is true. 5 equals 6. Okay. Now, I know that in this proof I'm going to have to assume that P of k is true for some natural number k, and then prove P of k plus 1 is true. So just to be clear, P of k is going to be the statement 1 times 1 factorial plus 2 times 2 factorial. Go all the way up to replacing n with k. So k times k factorial. And that's going to be equal to, on the right-hand side, k plus 1 factorial minus 1. Then we're going to need to show that P of k plus 1 is true. So P of k plus 1 is going to be this entire equation, but replacing each instance of n with a k plus 1. So that's going to look like 1 times 1 factorial plus 2 times 2 factorial, all the way up to k plus 1 times k plus 1 times k plus 1 factorial. Right, I've just replaced each one of these k's with a k plus 1. And that's going to be equal to, I need to replace this n with a k plus 1. So inside I'll have k plus 1 plus 1. That's k plus 1 plus 1, that's k plus 2 factorial, minus 1 on the right-hand side. This is just a little bit of scratch work to help me in actually writing out the proof later. All right, but one thing to notice is just like in the last video, in the last example we had, the only difference between the left-hand side of this first equation and the left-hand side of this second equation is I go one term further, right? This equation is going to go up to k times k factorial and then have one more term, k plus 1 times k plus 1 factorial, which means we're going to be using this statement here, which we'll assume to be true, and manipulating it so that it looks like this. All right, so we'll come back to those details momentarily. Let's try to prove this using the principle of mathematical induction. So, base case, we must show P of 1 is correct. P of 1 says 1 times 1 factorial is equal to 1 plus 1 factorial minus 1. I'm just really recreating the work that I did up here already. So this is just 1 is equal to 2 minus 1, which is correct. So the base case is true. All right, now we move on to the induction step, and let me go back really quickly to what that looks like. We said for the inductive step, we let k be some natural number greater than or equal to 1. We assume p of k is true, and then we show that p of k plus 1 is also true. So let's try it. Let k be greater than or equal to 1, and assume that p of k is true. So we can assume that this equation up here is correct. We assume that 1 times 1 factorial plus 2 times 2 factorial all the way up to k times k factorial is indeed equal to k plus 1 factorial minus 1. All right, now remember we call this equation here, we call this equation our induction hypothesis. Whole thing. Because this is the thing that we're assuming. Okay, now we must show that p of k plus 1 is true. All right, in other words, we're trying to show that this equation up here is correct. Now remember, the only difference between the left-hand side of pk and the left-hand side of pk plus 1 is you've got this one extra term tacked on to the end. So that's exactly what I'm going to do. Same idea as what I did in the last one. I'm just going to add this last extra term to both sides of this equation. All right, so using the induction hypothesis, and adding that last term, so that last term would be k plus 1 times k plus 1 factorial to both sides of the equation will yield the following. So start with the induction hypothesis because this is what we're assuming is already true. Right, we're assuming this is our induction hypothesis, that this is equal to k plus 1 factorial minus 1. And now what we're going to do is we're just going to add this last term, k plus 1 times k plus 1 factorial, to both sides. All right. Now, the left-hand side of this equation matches the left-hand side of the statement that we're trying to prove is correct. So all we really need to do is show that the right-hand side of this equation, this business here, matches the right-hand side of what we're trying to prove. If we can show that this here is equal to k plus 2 factorial minus 1, then we'll be done. We will have shown that p of k plus 1 is true, and we will have completed the induction step. So we must show that this right-hand side here, k plus 1 factorial minus 1 plus the red stuff, plus that k plus 1 times k plus 1 factorial, is actually equal to the right-hand side of the induction step, the k plus 2 factorial minus 1 to complete the induction step. All right, how do we do that? Well, the good news is we already have a minus 1 at the end, right? We have a minus 1 term here, a minus 1 term here. Let's not mess with those. Let's just leave those alone. So it's enough really to show that k plus 1 factorial and then plus k plus 1 times k plus 1 factorial, all this is equal to k plus 2 factorial. So I'm just going to rearrange this a little bit, put these two terms together and put the minus 1 at the end. So we have k plus 1 factorial plus this business, k plus 1 times k plus 1 factorial, and then a minus 1 at the end, just moving it around, is equal to k plus 2 factorial minus 1. Again, this is what we're trying to show. We need to show that this equation is correct. How do we do that? Well, this is what we're trying to show, right? That this start here, this stuff is equal to this. And I can rewrite this because I have a common factor of k plus 1 factorial. I've got a k plus 1 factorial term right here, and I've got a k plus 1 factorial term here. If those were just plain x's, you would know, oh, I can factor out an x. Same idea. You can factor out a k plus 1 factorial. So I'm going to factor out a k plus 1 factorial here and see what's left. I still have a minus 1 at the end. So if I factor out a k plus 1 factorial here, I divide it out, and all I'm left with is a 1. And if I factor out a k plus 1 factorial from this second term, all of this is going to go away, and I'm just left with k plus 1. And I know that this is going to be equal, I'm trying to show this is equal to k plus 2 factorial minus 1. Is it? Well, let's try and simplify inside. This is really going to give me k plus 1 factorial times 1 plus k plus 1. That is k plus 2. I'm just going to write it on this side just to try and remind you what we did in the last page. We still have a minus 1 at the end. We're trying to show that this is equal to k plus 2 factorial minus 1. Is k plus 2 times k plus 1 factorial equal to k plus 2 factorial? It is, right? Think about this as like 7 times 6 factorial is equal to 7 factorial. That's that stuff that we had said here. It's using this rule right here, but instead using it to say k plus 2 factorial is just k plus 2 times k plus 2 minus 1, or k plus 1 factorial. That's the same idea. So this is true. This indeed is equal to k plus 2 factorial minus 1, which is what we're trying to show it was equal to. All right, and thus we have shown that this equation here, or this left-hand side here, 1 times 1 factorial plus 2 times 2 factorial, all the way up to k plus 1 times k plus 1 factorial is indeed equal to k plus 2 factorial minus 1. And thus, p of k plus 1 is true. This completes the induction step. So, by the principle of mathematical induction, that statement p of n at the beginning, this equation here, is true for all n. All right, we'll do more videos, more examples of induction proofs in our videos for tomorrow, or for our next class.